Okay, today's video is about rates of convergence in the multivariate CLT for Levy processes without assumptions beyond the second moment. This is joint work with Jorge González Cázares at UNAM and David Kramer-Bang at Aarhus. So we start with a classical CLT when we take IID random variables in R, which are centered and have unit variance, and then the corresponding random walk scaled by 1 over square root of n is well known to converge to a standard Gaussian random variables n. The same thing happens with a Levy process, or continuous time process with stationary independent increments appropriately centered and scaled. Okay. Now, since the limit is nice, it's well known that the Kolmogorov distance, which is just the L infinity norm between the distribution functions of the pre-limit and limit random variables, converges to zero. The question really is how fast. And the Berry-Esseen, classical Berry-Esseen theory tells us that if we assume that the Levy process has 2 plus delta moments for some arbitrarily small but positive delta, then the convergence is polynomial of this rate with some universal constant c delta. Now, if we allow ourselves to sort of deteriorate this assumption and send delta to zero, then not only does the rate become unbearably bad, but also the constant is well known to explode. So the main question for us is, can we say something about this convergence rate only in terms of under the assumption that the variance is finite, okay, no further moments. In fact, we are interested in the multidimensional Levy case, where we consider not the Kolmogorov distance or the even multidimensional Kolmogorov distance, which in some sense is a special case, but really the convex distance, which is a natural distance in the Berry-Esseen, multidimensional Berry-Esseen literature, where the supremum is taken over all Borel measurable convex sets. Okay? So it will turn out that the answer to this is yes, we can say something, but it'll all be related to how we scale the process. Okay, so from there's the second question that we consider is can we say something about this convergence rate when we insist on using the classical scaling, right, not the modified scaling? Okay, so the first question, okay, is answered completely by this characterization theorem. It characterizes this theorem all Levy processes in RD that have a second moment. And it turns out that such a process, Levy process in RD has a second moment if and only if this convex distance of appropriately centered and scaled process or limit is integrable with respect to this measure dt over t. So in other words, this function divided by t is integrable at infinity. Okay, it's integrable at infinity. So here the centering is an arbitrary measurable centering vector, and b of t is a scaling matrix, which needs to be satisfied this analog of the slowly varying condition for matrices. Okay, so you see this b of ft multiply on the level of b of t to the -1. This converges to the identity matrix where v of f of t is a function that has the same asymptotic behavior as the identity at infinity. Okay, so these two conditions, so this convergence, this integrability of this distance is equivalent to the process having the second moment. And moreover, from proof, it turns out that if I take a b that satisfies this part b of the theorem, so this matrix valued function, then and center as I should, as I can in this case, because I know in that case the process must have a second moment, so it has a first moment, so I center appropriately, then this limit actually tends to zero. You see, this is not a direct consequence of the integrability here, because this is of course a continuous function, right? A continuous function that is integrable at infinity needn't tend to zero, but this one in fact does. Moreover, from the proof, it follows that if I'm in this case A, then I can construct this function, this centering function, natural centering function, and the scaling function, which is sort of modified square root t function, okay, by this matrix where this delta of t is the square root of sigma of t, where sigma of t is given by the Gaussian component, which could be 0 of my Levy process x, plus this matrix integral of the Levy measure of x on the ball of radius proportional to square root of t. Okay, so this is this sigma of t, and as t goes to infinity, this will converge to this quantity, which is well known to be equal to the covariance matrix of the process at time 1, which I denote by sigma squared, right? And this matrix is by our assumption assumed to be positive, definite, and non-degenerate. Okay. So this delta of t has a constant limit, right? And the proof of the theorem shows that these AC and BC can be used in this part B. So if I have a second moment, I can construct them, and indeed this function that I obtained, the corresponding function that I obtained, is in L1 lock, and of course therefore it will also converge to 0, and I will get a convergence, weak convergence. Okay, now. You see, I had this delta of t there. Now, if I change this delta of t and I just scale as I do in classical CLT, and then of course I substitute here the limit simply rather than scaling by square root of t delta t, or just by delta t here, then the question is this function in L1 log? So divided this distance, this convex distance divided by t, is it in L1 log? And the answer is, again, given by this theorem, it's a complete answer, and it says that it will be in L1 log if and only if the process at time 1 has 2 plus log moments. Okay, that's the condition. That's again an if and only if condition. Okay? So the question, the answer to the question 2 is no in general. Right? So the integrability of this in the square root t CLT is equivalent to 2 plus log moments of the process x at time 1. Right? While the second moment is sufficient if I scale by square root t delta of t. Okay, so in general, under this assumption only, but I don't assume 2 plus log moments, but only 2 moments, this scaling will produce faster convergence in the convex distance than the classical scaling, which is of this type, even though the sigma of t under the second moment assumption converges to this delta of t under the second moment assumption converges to the sigma. Okay. Now, a simple example: if you take a Levy measure that makes this integral infinite. Okay, so this is easy to see from the definition of the Levy measure and spherical coordinates and the Jacobian there. This infinite integral is well known to be such that to make the Levy process not satisfy the 2 plus log moment assumption. Okay, so in that case, this delta of t will play a role, and I will get a faster convergence rate in convex distance for this scaling. With this scaling, of course, with delta of t, you see, it converges to the identity matrix times some scalar, and it converges to it in some sense rather slowly. Delta of t converges to it as square root of log t. Okay. And so this theorem too explains why these Berry-Esseen type bounds under 2 plus delta moment assumptions have to deteriorate arbitrarily as delta goes to 0, you see, because when delta goes to 0, you're sort of breaking this barrier of 2 plus log moments. Okay, so nothing good can happen. Okay, now to put this thing in the context of the multidimensional domain of attraction, recall that X is in the domain of attraction of a standard Gaussian random vector Z in RT if there are two measurable, so a measurable vector function and a measurable matrix valued function, such that such weak convergence holds. Okay. Now this class has two subclasses, natural subclasses. If I look at the trace of this BT, okay, this can be either growing to infinity when compared to square root of delta t or not. And if it does not, then we say that we're in the domain of normal attraction. And if it does, if this lim sup is infinite, then we're in the domain of non-normal attraction. Okay, so these are sort of natural analogues of the one-dimensional definitions. So now it's not so hard to see that if X is in the domain of normal attraction, that X is in the domain of normal attraction, if and only if I have a second moment. You see, if I have a second moment, then my classical CLT tells me that I will be in the domain of normal attraction, because in that case, I know that I will be here scaling by 1 over square root of t times the covariance matrix of the process X at time 1. So this lim sup will be finite. Okay? And the implication in this direction really follows from the fact that component-wise, this kind of implication holds even for random models. Okay. Now, so for X in the domain of non-normal attraction, therefore, we conclude that it is not going to have a finite second moment. Okay, in other words, this Levy measure doesn't have finite second moment. And also, of course, by definition, this lim sub has to be infinite. And now our theorem 1 therefore implies that if I am in the domain of attraction of Z, but in the domain of non-normal attraction of Z in particular, then what happens is that this distance for these for any pair of centering and scaling vectors and matrices cannot be integrable with respect to the measure dt over t. Okay, it cannot be integrable. So in other words, you see, here I'm looking at the Kolmogorov distance, but this is multidimensional Kolmogorov distance which is bounded below, just a supreme over hyperray, so it's bounded bounds below the convex distance. So this means that the convex distance here, right, the convex distance here, cannot be upper bounded. The convex distance here cannot be upper bounded by a function that is integrable with respect to dt over t. Okay, so if I'm in the domain of non-normal attraction, then some slow convergence is going to happen, right, for sure, because there is no integrable upper bound. And this is sort of reminiscent to our recent work on the stable domain of attraction in the short time domain, and where it was shown that slowly varying components really can change the rate of convergence significantly in these domains of attraction. Okay? Now, to conclude, let me say a few words about the proofs of these theorems, right? So, theorem 1 is sort of equivalence of the second moment and this integrability, okay, of the convex distance. Now, the implication from A to B really depends on the multivariate Berry-Esseen applied to appropriately truncated Levy process, and we also depend on this multivariate mean value theorem and need to generalize a limit theorem for multidimensional Levy processes in the small time domain of attraction from Asmussen's classical paper of Asmussen and Brzezinski. Okay. Now, once this implication has been established, then one can prove this theorem 2, in fact, right, which says that 2 plus log moments is equivalent to a classically scaled sort of pre-limit object for the convex distance to be integrable at plus infinity with respect to the dt over t. Okay, and so how does that work? Well, this distance that we're interested in by triangle inequality, we can compare it to this bit and this. Okay, so and this part is exactly what is covered in the implication from A to B in theorem 1. Okay, so this is always going to be integrable under the L2 assumption, and then this term needs to be considered, right? So here you see analysis of this convergence, integrability of this distance needs to be done, and the key thing here is the thing that causes complications is that here this delta of t is scaling each component differently, okay, possibly, depending on how the Levy measure behaves, because we make no assumption on the Levy measure, of course, beyond the second moment assumption. So what that means is that one needs to sort of be careful and sort of apply carefully the multivariate mean value theorems for matrices. And now finally, the hardest perhaps step in the proofs, in all these proofs, is the implication in theorem 1 that says that if the convex distance for some centering and scaling vector and matrix is integrable, then the second moment is finite. And the basic argument for this sort of shows that this integrability cannot hold if this second moment is infinite. And so the inspiration really for this was comes from these classical but not so well known works of Chris Heide from late 60s and early 70s, where he proved similar assertions for one-dimensional random walks. Of course, the generalization to continuous time in multidimensional setting are non-trivial. So the continuous time, of course, gives us trouble. That, for example, the summability of the distance immediately implies that the sequence of distances goes to zero in the discrete time case. Well, of course, this is not the case, and therefore, of course, also sort of weak convergence. Well, in continuous time, of course, this is not the case, because a function can be integrable without it tending to zero, and in fact, it's only a consequence in theorem 1. And the multidimensional situation is really, one needs to consider, of course, all convex sets, because we're looking at convex distances. Okay, so yes. Now, to conclude, just here are the references. This is the Asmussen-Rosinski, well-known Asmussen-Rosinski paper on Gaussian approximations. This is our paper, a recent paper on the stable domain of attraction, where it was shown that slowly varying functions really play a crucial role in the convergence rates. And these are the two papers of Chris Heide, where similar questions were studied for random walks on R. So thank you for your attention. The paper is available on arXiv, and it has the same title as